The James Webb Space Telescope was a partnership, multinational, all different companies, suppliers, came together to make this thing happen. Suppliers all over Europe, all over the United States, South America, came together to make this work. There's thousands of people who made this telescope possible, and many, many people who spent their entire careers only working on James Webb. Which, you know, for $10 billion of our national budget, I would hope that this thing is bringing awe to every one of you. It's bringing us the next great views of the cosmos, the next generation, all of the nice space calendars, space backgrounds, with all of those Hubble pictures that we're so used to. We're going to have a whole bunch more coming up real soon. I can't see this. Okay. Just like these first pictures that you see here today. These are a couple of the first images that James Webb came back with. We launched on December 25th, 2021 on Christmas morning. How many of you guys woke up early to see James Webb launch? Oh my gosh, that warms my heart, y'all. Thank you for being there to support. Hold on. Okay, so I want to talk to you about some of the different parts of James Webb. We have three main pieces that go together. I mean, hundreds and hundreds of thousands of pieces make up James Webb, but they all kind of fall into three different categories. We have the spacecraft bus here at the bottom. For those of you who can see the screen, the spacecraft bus holds most of the internal organs of the satellite. Most satellites have a lot of the same internal organs, right? So we have the batteries, the thrusters, the star trackers, the communications between Earth and the telescope, and then, but that all has computer electronics in it. All of that generates a little bit of heat, which is a problem because we are an infrared telescope. All of the instruments need to be kept super, super, super cold. We're measuring heat. So we have the second part, the sun shield. That protects the internal instruments that are on the back of the mirrors up here from all of the heat coming from the sun, from the heat coming from the internal instruments. It's so sensitive that the telescope instruments will pick up the heat generated, the little bit of heat generated by the electronics in the spacecraft bus. So the sun shield is super, super important. Okay. One of the things that makes James Webb special is the fact that it is an infrared telescope. So we have Hubble that looked at the visible light spectrum. We have Spitzer, we have Chandra. All of these different instruments work together to look at the same objects in the sky. To look at the same objects in the sky and collect different pieces of data that can all be put together to make a fuller picture, to give us more information all put together about the celestial object that we're looking at, whether it's an exoplanet or a galaxy. If you want to see some differences between infrared and visible light spectrum, these were actually both taken by the Hubble. But you can see on the right the visible light spectrum image that was taken, which is very pretty. We love that image. But then closer to the IR spectrum that we're looking at here. And we are looking past the space dust. We're looking further into space, further into the past. Okay, going back to the sun shield a little bit. Here's a picture of the scale model of the sun shield. There are 5 layers that are all made of a super reflective material called Kapton. Kapton that we're using is actually thinner than a human hair, but very, very durable. It's made up of 5 layers because the hot side will always face the same way, towards the sun, towards the earth. And then whenever the heat from the sun hits the bottom of the sun shield, some will get reflected, but then some will get absorbed and hopefully radiate out of the sides. And the scale of this thing is massive. If you take the sun shield and measure it, it is about the same square footage as a tennis court, whenever it's completely stretched out. So at a certain point, I got to climb up into the middle of it and look around. That gives you a good scale of it. I wish I could have brought that here for you guys to experience today too. The sun shield is so big, and the whole thing needs to fold up to fit inside of the fairing of a rocket to get up into space. So for the sun shield to unfold, it needs to be pinned in certain locations. That was deployed and stowed many times for testing. And every time we had to stow the sun shield, we had to put little pins in there to hold it in place. And to give you a bit of scale, the sun shield, if you took a king-size bed sheet and folded it up really nicely and put a needle straight through the middle, through all of the layers, took the needle out, unfolded the whole thing, folded it back up, you would have to get all of those holes that the needle went into in the same spot and put the needle through the same hole. So that's what our technicians had to do many, many times during testing. So the sun shield is so good at its job that on the hot side, that's always going to be facing the sun, always going to be facing Earth. The average temperature will be about 185 degrees Fahrenheit, and it blocks so much heat in the vacuum of space that it keeps the cold side at about negative 380 degrees Fahrenheit. So blocks a lot of heat. You can kind of use this technology, some ideas from this technology here at Burning Man. Whenever you take a reflective, like Mylar space blanket, see how that protects from the sun? Put some space in between that and your tent, and you'll get a lot more heat blockage because the air can radiate out the sides. So take that home. And now, the most recognizable part of James Webb is our beautiful hexagonal pieced together primary mirror. The mirror is big as hell. It has a 6.5 meter diameter and has 6.25 times the amount of light collection area that the Hubble Space Telescope did. So that gives us a wider field of view and obviously able to collect a lot more light. These mirrors are made out of a material called beryllium, which is known to be super steady at different temperatures. It's really strong. You know how when a cheap baking sheet in the oven, it like pops and warps whenever it heats up and cools down, heats up, cools down? Beryllium is really good for that. So they got giant chunks of this super hard to work with material beryllium and then shaved it down to be the exact right focus that we needed for each of the mirrors. And then if you look at this picture over here, we machined out a ton of the weight, most of the mass out of the back to keep it lightweight, to keep it able to be launched and go up to space with less fuel. As a comparison, the Hubble mirror is right here. And each of the mirror segments, there are 18 of them, have been coated in gold. Which, does anybody know why they chose gold instead of silver like the Hubble? Anybody? Katie? Correct. Gold is the best reflector of infrared light. Silver is the best reflector of visible light, which is why we use silver for like our mirrors, if you think of like chrome. But gold is the best reflector for the infrared light. And one of the reasons why this project was so challenging, NASA wanted a big-ass mirror, a big-ass sun shield, and there is no rocket on Earth that is big enough to put that thing out into space the way the Hubble was. Hubble was just kicked out of the space shuttle, and it had a solar array unfold, and that was pretty much it. But we had to make James Webb in order to fold up into a rocket fairing like you see here, and then transformer out, like do a complete transformation, unfold all of these different parts. There were hundreds of deployments that needed to happen once it got out into space to create the full picture, the full space telescope. And this only had to work once. James Webb deployments only technically had to work one time, from the time that it separated from the rocket fairing to the time that it got out to its orbiting point, about a million miles away. However, none of those deployments could go wrong. We don't have another shot on this. I don't know how many of you are familiar with the Hubble servicing missions, but we went up a couple times to fix some things that weren't exactly right with the Hubble. We do not have the opportunity to do that with James Webb. So we had to get it right the first time. So we tested the fuck out of it. We made sure that everything worked many times. All of the deployments were set to be automatic because obviously it was going to do that itself up in space. But all of putting it back, all of the stowing to get ready for the next deployment was all done by hand by many of our very brilliant mechanical technicians, which I had the pleasure to see many times. That was really cool. So before it goes out to space and starts all of these awesome deployments, to test the shit out of it, we have to kind of simulate the explosion that it's going to be on top of, right? It can't just, lightly get kicked out to space. It sits on top of an explosion to get out there, and there's a lot of forces that it experiences. So we have a couple of environmental testing procedures that we lovingly call shake and bake. We have vibrational testing, where we shake it in 3 different axes all over the place at all different decibels, and then put the whole thing into a giant acoustic chamber. This is the largest acoustic chamber that we could find. They close it, fill the whole thing with nitrogen, just the way the space fairing, the rocket fairing was, and then blast noise at it to simulate the really slow, tiny vibrations that it's going to experience, along with the vibrational testing. And then also the TVAC testing, thermal vacuum testing. There is actually not a thermal vacuum chamber big enough in the entire world for the entire James Webb fully deployed to be tested. So we had to test it in 2 different parts. This is OTIS, or the optical part, the mirrors and the space instruments behind, that were tested at Johnson Space Center. They fully refurbished an entire TVAC chamber specifically for Webb. It was historical and used on the Apollo missions. So we also tested the spacecraft bus and sunshield in a really cool thermal vac chamber to make sure all of the instruments would work whenever we got out in the cold. Then we come to the transportation. This is my wheelhouse. I love logistics. I love transportation. I'm a huge logistics nerd, and this particular project was really challenging. We had some special things to consider. It would have been really easy to ship this whole thing just to Florida, but because James Webb was a partnership between NASA, the Canadian Space Agency, and the European Space Agency, we shipped it all the way down, I don't know if you can see here, all the way down the coast of Mexico, through the Panama Canal, and around to the other side of South America to French Guiana. That is where the European Space Agency launches the Ariane rockets, and it was quite a task. They shipped a lot of our support equipment. We had many shipping containers, like you see out here, full of support equipment that we needed to take out there, and also had the added complexity of that being international and all of the fun paperwork that comes with all of that. So then on Christmas morning last year, we launched. Super exciting for a lot of people. A ton of people tuned in. Actually, on Christmas Day, hashtag JWST was the 2nd most trending hashtag on Twitter, next to Christmas, obviously, which made all of us proud. And Ariane, the rocket provider, actually did an absolutely stellar job at launching this thing. The lifespan of the telescope is based on its fuel capacity, so how much fuel it uses. And the more far off the rocket was in launching, the further it put it on its meant trajectory. the less lifespan that Webb would have had. However, Ariane did such a kick-ass job at launching this thing that put us on almost exactly the right trajectory, made us use significantly less fuel to get back on track to correct for that, and therefore doubled the lifespan of the telescope. So go Ariane, kick ass. This is the last view that we saw of James Webb, one of the last views. They had a camera. We don't have any cameras on the actual telescope, so they were just using some sensors to make sure all of these deployments were on track happening. But this is the actual last visual that we got. The camera was actually on the last stage of the rocket. And because Ariane did so well in their launch, our solar array is the first deployment that was supposed to happen either when we were on the exact right trajectory or 30 minutes after launch. And nobody really expected it, but before it went out of view, you can see the solar array just like slowly popping out. Very exciting. There's people who have spent their entire career just on that solar array, and I know they were absolutely elated to see that thing deploy properly, deploy on time, and for us to be able to see it. So all of that brings us to the lovely first pictures that came back from James Webb. The deployments went spectacularly, to most everyone's surprise, and we are starting to get these incredible pictures back to give us the next generation of views of the cosmos. That's about all I have. So thank you very much.